So the modern concept of atomic structure. The electrons are found outside the nucleus, and they're negatively charged. The protons are in the nucleus. They have a positive charge, which is equal in magnitude to the electron's negative charge. So their charges balance out. The neutrons are in the nucleus, and they have no charge, and their mass is essentially the same as a proton. So the nucleus is small compared to the overall size of the atom. I gave you that analogy of the green pea and the football field. Would you say the nucleus is small relative to the size of the atom? Yeah, it's kind of an understatement. It's extremely dense. I gave you that analogy, kind of jumped the gun on it, but extremely dense. Almost all the mass of the atom is in there. Oh, here's the table I thought didn't exist. Protons, neutrons, electrons, and so their relative mass, and that's just relative. So they're saying, well, if the electron had a mass of 1, then the proton and the neutron would have masses of 1,800, so almost 2,000 times bigger. That actually has no units. That's relative mass. Just saying, well, if this was 1, what would the others be? And then there's the charges. Electrons are -1, protons +1, neutron no charge at all. So why do different atoms have different chemical properties? The reason that the atoms have different properties is because of the electrons. So we just learned that the nucleus is in the middle of the atom. What's on the outside of the atom? It's the electrons. The electrons are what interact with other atoms, and that's where our properties come from. So it's the electrons that give rise to the chemistry of the atom. The electrons intermingle when atoms combine to form molecules. The number of electrons determines the chemical behavior. And we'll learn more about why that is later. Now, I mentioned isotopes. There are isotopes. You can have atoms of the same element. They're always going to have the same number of protons. It's the number of protons that identifies an atom as an element. Hydrogen, all of them have 1 proton. Carbon, all the carbon atoms have 6 protons. But they can have varying numbers of neutrons. They're going to have almost identical chemical properties because they're going to have the same number of electrons. The electrons and the protons are the ones that have charge. So if you have 6 protons, you have to have 6 electrons to have a neutral atom. You throw an extra neutron in there, and that's not going to affect the electrons at all. And so that's why the properties are almost the same. These elements that we find in nature are going to be a mixture of isotopes. They're not just going to be one single isotope. It's a mixture. So here's just an illustration, 2 isotopes of sodium. So here's the nucleus, and these are not drawn to scale. Here's the nucleus. For this one, this has 11 protons and 12 neutrons. 11 protons, therefore it has 11 electrons. And this isotope also has 11 protons and 11 electrons. 11 protons is what identifies that as being sodium. But this one has 13 neutrons. So they have the same number of protons, same number of electrons. The only difference is this one has 2 extra neutrons. 1 extra. 13 minus 12 is 1 extra neutron.
How do you know how many they have?
That's a good question. How do you know how many neutrons they have? I probably was supposed to say this and forgot. On the periodic table, there's a whole number above each of the element symbols. That's the number of protons. So above the symbol for carbon, C, is the number 6. That tells us there are 6 protons. If there are 6 protons, there are 6 electrons in the atom. How do we know the number of neutrons? We can't tell from the periodic table. They do experiments, basically, and they can figure out what they are, or we can be told by these isotope symbols.
Does it tell you how many isotopes each element has?
Not on the periodic table, no. There are some that only have one, and some have several. And it just kind of varies, and it's not predictable, and I won't ask you to predict it. But we use these symbols like this, where X is the element symbol, A is the atomic, sorry, not the atomic number. That would make too much sense. Z is the atomic number. A is the mass number. The protons and the neutrons are the ones that have mass. And so if you put those together, we get the mass number. And that's going to be close to the atomic mass of an atom. So let's look at an example of this. So here we have carbon 14 and carbon 12. C is the symbol for carbon. It's the same on both sides. 6 is the atomic number. On the periodic table, carbon 6 protons. So both of these isotopes of carbon have 6 protons. The difference is in the neutrons. And if we take this is like it's set up for subtracting, isn't it? 14 minus 6 is 8. 12 minus 6 is 6. Oh, that disappeared. Nice. The mass number is 14. That means there's 6 protons and 8 neutrons. On this guy, 12, 6 protons and 6 neutrons.
Is that what the red is on the periodic table up there, underneath the C?
No, that's the average atomic mass, and we'll talk about that
So on
later.
this example, that would apply.
That doesn't apply, no. So here we have the 8 and the 6. So that's enough to make you dangerous.